So good morning, everyone. So as you notice, today we'll start a new chapter, and it's called Electromagnetic Induction. And from the name itself, you notice it is electro word also as well as magnet word. So this one topic which connects or electricity with magnetic properties. And a major part of this chapter, or maybe the beginning of this particular topic, is started with Faraday's law. Okay, so initially we're going to study about Faraday's law. Faraday law is based on series of experiments what he conducted, and based on those experiments, like many other physics law, he deducted a law which is experimental law, and which formed the basis for electromagnetic induction. And see, if some of you read this anecdote, soon after he came up with this law, some reporter or whatever, somebody asked him, what is the practical application of the law? To which he responded, there's something, if a child is born, if somebody asks him what this child is going to do to the world, we won't know what the potential the child may have. Only time would tell. And later on, over a period of decades and centuries, what we find, the law which is started, which looks so simple, it formed the basis of entire power generation. Most of the power generation is based on similar principle, and that's what we're going to learn now in this chapter. So Faraday law, what was the kind of, he did number of experiments. So we'll take up some illustrative experiments. So something like this, let's see. So in this case, what we see in the figure here, this also is one of the several setups we can use to understand Faraday law. So what we see here, see if you look at this figure here, there's a circular coil here. And the circular coil, any circle will have an axis. This is the axis of the circular coil. And the circular coil is connected to a galvanometer. And this galvanometer is bidirectional. It means it can swing in both directions. So current can flow in this direction, current can flow in the opposite direction. And then a bar magnet is placed on the axis of the conducting circular loop. And circular loop is connected to a galvanometer. This is a galvanometer. So, and this is the bar magnet. So this is very simple arrangement, and it's very easy to have this experiment. It's very easy to conduct this experiment without any sophisticated equipment. Okay, so what are three figures are shown here? First figure, the figure A, when the bar magnet is at rest. So this bar magnet is just held here on the axis of the circular coil, and it is not in motion. And what we observe here, not very surprisingly, when the bar magnet is at rest, no current in the loop. And when there's no current, of course, we know there's no current because there's no deflection in the galvanometer. This is the first setup. Then what I did, second setup in part figure B. What we notice here is this bar magnet is moved towards the coil. And it is moved along the axis towards the coil, north pole facing the coil. So when the bar magnet is moved towards the loop, suddenly what we find, this galvanometer shows deflection. The fact that galvanometer shows deflection indicates presence of current. So what we notice here, this motion of the bar magnet created current here. So this magnet here created a current which is electrical property. That's how we link two things together. So this indicated the magnet is linked to current in some way, or other way what you're saying now, the magnet can create electric current. And a similar way, if we continue the experiment in figure C, what we notice, in this case, this was at rest. This was moved towards the coil. And third case, when the bar magnet is moved away, again there's a current, but this time current is in the opposite direction. If it showed deflection in one direction, this case it showed in the opposite direction. What this indicates, whichever direction the current was when it was moving towards the coil, when it is moving away, the direction of current was opposite. And what we observed, the current lasts only as long as bar magnet was in motion. So if we move the bar magnet, again immediately come to stop. Moment the bar magnet comes to stop, the current also drops to zero. So what is causing the current here in the loop is the motion of the bar magnet. And deflection was larger when the bar magnet moved faster. So if hand you move it slower, the current was smaller. If you move the hand faster or you give higher velocity to the bar magnet, current was more. These were the observations, and something similar. He conducted a number of experiments, and what this person Faraday had, I won't say he had not much of knowledge of mathematics, but all his recording or whatever experiments he conducted, all his notes are free of any mathematical expression. So this is something, had all scientists been like Faraday, perhaps we would have seen very little of mathematics, but in fact, without mathematics, science also, physics would not have progressed. But this particular thing he did without much of mathematics. And based on this observation, he deducted a law which captures whatever is happening here. The law is something like this. Whenever magnetic flux, we have come across this word flux previously also, we'll discuss this in more detail. Whenever the magnetic flux through an area bounded by a closed loop changes, there is an EMF induced in the loop. And what is the EMF induced? This is a formula he gave. Induced EMF is equal to negative of rate of change of magnetic flux through the loop. And that's what we'll try to understand what this expression indicates. What is this term phi here? Phi is magnetic flux. And we have come across the flux before. We have done electric field flux. Electric field flux is a dot product of electric field and area vector. Magnetic field flux will be equal to dot product of magnetic field dot area vector. Exactly same thing what we have done in case of before Gauss law. We have done electric field flux. So something is very similar. And what is the circle indicate here? Is over a closed loop. Okay, this is over a closed loop. B dot dA, not a closed surface. This is over a closed loop. It is equal to the flux of magnetic field through the area. So we'll see later. So we already know how to calculate flux for electric field. Similar way, you can calculate the flux due to magnetic field as well. So, does it explain why, if we move the bar faster, is the EMF induced more, and that's why the current is more? Of course, when you move faster, see, if you move the bar magnet by a particular distance, there's a particular change in magnetic field and magnetic field flux. But if we move it faster, that change happens in a smaller time, rate of change becomes more, and hence induced EMF is more, and the current also is more. That was what was observed. Perhaps those kind of observation led him to this law statement. Okay, what would the unit of magnetic field flux? Unit will be equal to, what is this one? This is equal to BA into cos theta. So unit has to be equal to product of unit of B into area. Unit for B is Tesla and area is meter square, and we give it a name called Weber. The Weber is the unit of flux. So from this only we can also find an alternate unit for Tesla. What is the alternate unit for Tesla? Weber per meter square, which you might have come across in the previous chapters also. Many times magnetic field given. Yes, Vignesh.
Sir, why the negative sign, sir?
We will come to negative sign also. No, we'll come to negative sign. Why there's a negative sign? That actually this, most of it is based on two laws. Both laws are very simple one. One is Faraday law, other is Lenz law. The Lenz law indicates negative sign. We'll come to the next slide. Yes, good question. Why negative? We'll discuss what does negative signify here. So in terms of unit, this is flux. Flux we know this is called Weber, and Tesla also can be. We can use a unit called Weber per meter square for magnetic field. So this induced EMF, but why the current is, so if so the circuit or loop behaves as if there's a battery of EMF equal to E, and we know when this EMF it may result into current. And what is the current equal to? Current is EMF by R. So if the loop is a conductor resistance R, if induced EMF is E, current will be equal to E by R. That's what it is written here. Then there's induced EMF will produce an induced current. So change in flux creates induced EMF, and induced EMF produces induced current. How much will be induced current? EMF by R, R being the resistance of the loop through which flux is changing. So this is basically same thing, extension of the same law. Okay. Thus induced current. Now we come to in terms of direction. We have seen in this case, if it is brought closer to the loop, the direction of current is one sense, but we take it away, direction of current is in the other sense. That we can understand using Lenz law, and we also get a sense of why there's a negative sign. What does Lenz law say? There's induced current in the loop. The direction of induced current is such that it opposes the change that has induced it. So basically, what is the key word here? It opposes. So that's why whatever it is, this is a negative sign. Negative sign indicated. So if EMF is produced because of change in magnetic field flux, it will oppose it. So negative sign is only to indicate that effect is opposite. And that opposite sign we'll understand in terms of number of applications. So one by one, we'll try and understand how to find the direction of induced current. If we find direction of induced current, we'll understand direction of EMF. Okay, so let's see what does this mean. This sentence by itself may not give a lot of clarity, but when we apply this law in certain cases, we get a better understanding of what does opposes mean. Okay, so when flux changes, anything changes, two things can happen. Flux is a scalar quantity. So we are not talking scalar quantity. So change could be two types. Either it could increase or it could decrease. So there are only two possibilities when it changes. Let's take first case. First case, if it is increasing. Then suppose the flux is increasing. So how do we oppose the increase? The induced current, by inducing current, which produces a field, induced field, in the opposite direction of the field which is producing varying flux. So we'll understand that also. If something is increasing, how do we oppose that increase? There's some field here. If this something is increasing, you can oppose by inducing something which is in the opposite direction. So what will happen if you take the net? It tends to decrease it. So it is opposing the increase by creating something which in the opposite sense, I think, which makes common sense. And similarly, other way around, if flux is decreasing, it opposes by inducing current which produces field in the same direction. Let's see how we apply these two statements in terms of a simple example. Okay, let's take first example. Suppose I view from here. Okay, I view from here. This is where the observer is. If you view from here, how the field lines will be? See the field, this is North Pole. Magnetic field will be like this. So if I look at the loop, if I stand from here, I can see like this. This is the loop here. And the field created by magnet is of this nature. I hope this point is clear. If it is North Pole, the field here will be like appear like it coming towards you. It will look like a dot. Had it been South Pole, it would have been reversed. So this is how the field is, and so flux is getting created. Now take case B case here. So B case, what is happening here? Is the flux increasing or decreasing? So there's a field here. There's an area here. There's a loop which has some area. There's a magnetic field. There's a field also, and there's a flux. We calculate some flux here. What would happen if I bring this magnet closer, bring it close to the loop? Why there will be change in flux? Can someone think of what is the reason of change in flux? What is changing here? What is flux equal to? In terms of magnitude of flux, flux is equal to BA cos theta. Which term is changing here? When the magnet is brought closer to the loop. Actually, what is happening? B is increasing. As the magnet is brought closer, close to the magnet, magnetic field strength will be higher. So when in case B, since B is increasing, what happens? Flux also is increasing. The flux also is increasing, so it is dot and is further increasing. The induced current will oppose the increase by creating a field in the opposite direction. So this will be the direction of induced field due to induced current. So which kind of current? Should the current be clockwise or anti-clockwise? Suppose the current had been anti-clockwise. Anti-clockwise current will create a field which is in the same direction, which will further increase this flux. So this is not correct. So what has to happen? The direction of current has to be clockwise. Like this. Clockwise. If direction of current is like this, the induced field will be cross. What will happen if we take net effect? This dot is increasing. If we create a cross field, it will tend to decrease the overall field, which is this point here. So when flux is increasing, if flux is increasing due to dot field, it will create a cross field. The current will be such that induced field is of the nature of cross. Is this point understood? Pranav? Pranav Soma?
Yes, sir.
Okay, so can you tell me next case what will happen? So is this point also clear in induced field? Now let's case C case. This is the which case? Third case. Now what is happening in this case? Which side is the magnet being moved?
Towards the
This case. Third case.
away.
Away from it. So what is this? Let's write one by one. In this case, magnet is moved away. What is the effect of magnet being moved away?
The current will be.
No, don't jump directly. Next thing, step by step. If I move the magnet away, what will be the effect of magnet being moved away? Pranav, can you think of what will happen? Ashley, can you tell me what will happen if magnet is moved away?
The induced field would try to nullify.
Don't jump. No, basically what will happen? See, there's a flux created. What will happen? B will reduce. Magnetic field in the region of loop. Is that correct or not, Pranav?
Yes, sir.
In the region of loop will decrease. Then what is the effect of decrease in magnetic field, Pranav?
I mean, the current will produce.
No, again jumping.
Flux
Flux will decrease.
Flux
Is it not? If V decreases, what will happen? Flux is decreasing. If flux is decreasing, it means now what has to happen? How has to get? So induced current must create field in the same direction. Is it all making logical sense? Field in the same direction. So which direction is that? Which is the direction? This direction. So that has to be the direction of induced field. Are you understanding? There's an original field present, there's an induced field. So which direction the current has to flow? The current has to flow in this direction. Hence, the current is in the anti-clockwise direction. All steps, Karthike, all steps are clear?
Yes, sir.
Kaushik?
Yes, sir.
Okay.
Sir,
Yes?
I didn't understand if the field is decreasing, why the induced field should be in the same direction.
Tell me, okay. What if a field is decreasing? Okay, suppose it was 10. Okay, if it has become 8. Okay, so it is decreasing. So how do I oppose it? Oppose the decrease? Suppose I add. Okay, let me put another way around. Suppose you have bank account. Okay, bank account you had 100 rupees. Your money has dropped to 80. How your father will oppose the increase? Oppose the decrease by adding money or withdrawing money?
Adding.
Adding money. So if it is decreasing, what do? You add something. If it is increasing, what happens? From 100, it has become 150. How do you oppose the increase?
We decrease. Withdraw.
Something. So here also, which direction the field is? Field is in the dot direction. If induced field also is in the same direction, what will happen? It will further increase. It is acting in the direction of increase. So how should I oppose the increase? By creating something which is in the opposite sense. Does it sound logical?
Yes.
Again, think of it. Shall I go through that once again?
Yes, I got it.
Okay. So I hope everyone clear. We'll go do a number of times. So something similar we'll do in other cases as well. I'll come to one more case now. So there are a number of ways it can be done. What is the second we can think of? Let's look at this. In this case, what we have done here, again, we are learning the application of Lenz law. So there's a current carrying conductor. There's a wire which is carrying current I. And we have placed two loops here. These two loops have no battery connected. So logically what will happen? The battery is not connected. Both the loops will not have any current. But if this current is increasing, can we find the direction of induced current in loop A as well as loop B? Okay, so let's look one by one. Okay, now whom should I? Preetham?
Yes, sir.
Can you speak now? Any problem?
No, sir, I can speak.
So let's see. I want to find out direction of induced current in the loop which is on the right hand side. Okay, I want to find out direction of induced current. Can you think of how should I find direction of induced current in loop B? How is the loop placed such that opposes change induced it? The two conducting loops are placed close to the current carrying wire on either side or lie in the same plane. Can you think of method how would I find out direction of what I need to find before I find the direction of induced current in the loop? So Pritham, can you think of any method? Any logic? Not clear? Okay, let me ask someone. Bhagishri, can you tell me now? What we have to think of first?
So the field is increasing, so we need to find a way.
No, so basically, first of all, current field is increasing. And so basically, see, it all depends on change in flux. So we need to understand: is there a flux through this loop?
Yes.
Is there a flux? Which direction the field is? So for flux, there has to be presence of magnetic field. What is the direction of magnetic field through loop B? So first we need to find out, is there magnetic field?
Yes,
Direction of magnetic field through B. Can you tell me direction of magnetic field through B?
into the page, sir.
Into the page. So I understood what is direction of magnetic field. This is the direction of magnetic field, which is causing flux.
Yes,
Right? Then what is happening as current increases, what will happen? B also will increase. As B increases, what will happen? Phi also will increase. If phi increases, then what happens? What is the next logical step if phi increases?
Induced field should oppose it.
Field, or I can use the word induced field. Then an induced field must be in the
Opposite direction.
opposite direction. Then only it is opposing. It is increasing. It will oppose the increase by creating something in the opposite sense. So basically, I can write. Hence, this implies Bi must be in the opposite sense. So what sense of B induced field has to be? Since this is dot, this has to be in the dot direction.
Yes.
So what must be the direction to create dot field?
Anti-clockwise.
Okay. Induced current. Direction should be such. To create dot Bi. And dot Bi we know, so this is the direction of induced current. Okay. Now, Gayatri,
Yes, sir.
can you tell me how to find direction similar way? Can you tell me for loop A? Step by step, same method, one by one. I want to find out direction of induced current in loop A now. Can you similar way, have you followed these steps here, all logical steps?
Not clearly, sir.
Okay, not clearly. Okay, so direction of induced current in A. So let me ask someone, how many you can explain? Can you raise your hand? How many you can explain how to find direction of induced current in A in similar sequence as we done previously? How many of you can do that? Let me ask some of those who can do that. Okay. Atika, Shriya, okay. Hemant, can you tell me step by step? Hemant? Direction of induced
Yes,
current
sir.
in A. Try to tell me step by step.
First, the direction of.
Okay, leave it. I think if there's a background sound in your case, I'll ask someone else. Okay. Can you, Shriya, can you tell me step by step how to do it?
Yes, sir.
Tell me.
Similarly, first we need to find the direction of magnetic.
First we need to find direction of magnetic field. You know what is it? Because first you have to think of flux. So direction of field through the area bounded by A. What is the direction of field?
Outwards.
I find the direction of field is outwards, which is outwards. Then what I find? Why is it? So this is creating flux. But we are entering a change in flux. Why the change in flux? Here current is increasing. What is the effect of increasing current?
Magnetic field.
Magnitude of field increases. If field increases, what is the effect of increasing magnetic field? flux increases. Are you clear? So the flux increases. As the flux increases, it means what has to happen? How do we oppose this increase in flux?
Induced current is acting, which will decrease.
Decrease the, which it will tend to oppose the increase by creating something in the opposite sense. So that's why the overall effect will reduce. Opposite sense. It will oppose by it will oppose by induced field in opposite sense. This is pretty clear. Gayatri, are you paying attention now?
Yes, sir.
So far followed?
Yes, sir.
Yes. Which sense it will be? So this already dot. So what is the opposite sense? This has to be induced field has to be cross. So what must be the direction of current so that induced field is cross? This is the direction of current. So what will happen on the right hand side? This is the direction, and left hand side this is the direction of current. Are all clear? Kartikeya, you are clear?
Yes, sir.
Okay. So this is something, so similar way, if I mark direction of induced current in the loop, I is increasing. We have done both. What happens to the direction of induced current in the loop if I is decreasing? Direction of current is same, but now it is decreasing. All of you think in your mind, how do you find direction of induced current in both the loops? How do you find the direction of induced current in both the loops? Current is decreasing. All of you can easily find. First, let me mark the direction of field here.
Yes, sir.
This is the direction of field here. All of you can do it. This is
Yes,
direction.
sir.
And it is decreasing. It is decreasing means induced also in the same direction. Since there is a decrease in B, which leads to decrease in flux. So it will oppose by, how do you oppose the decrease? Oppose the decrease by creating induced field in the same direction. Right? Induced field in the same direction. So here also the induced field will be in the same direction. Here also induced field will be in the same direction. This is the direction of induced field. This is a field which is causing flux, the original field. If it is in the same direction, it is easy. This will be the direction here. And this will be the direction here. So you clear? Okay, I'll ask one more question. See, okay, so there's one more. See here, third question, I'll make change in the same figure. Let's say the current is not increasing or decreasing. Current is constant. Current is constant. This is loop A. What I do, if I start moving this loop away from the wire, if I move it away, will there be any induced current in the loop? If I move the loop away, what is the effect of moving it away? Okay, let me ask some of you. What is the effect of moving it away? Anvita, can you tell me what will the effect of moving the coil away? I'm moving the coil A away from this wire. Current is constant. Current is not changing. Can you think of what will happen if you move this coil away? Anvita?
Yes, sir.
Yeah, tell me.
So I'm not sure.
Not sure. Okay. Disha, can you tell me what will happen if you move the coil away?
Yes, sir. The magnetic field will decrease.
Yes. Okay. First of all, so basically, move the away means distance is increasing.
Yes.
Anvita, pay attention. Distance is increasing. Then what will happen? It was earlier it was some distance. Distance increases. As the distance increases, what will happen? B will decrease. So B depends on field due to current I, because we are always looking at what is the field of flux. B will decrease. If B decreases, what is the effect of decrease in B?
Change in flux will decrease.
The flux also will decrease. If B is decreasing, flux will, because other things are not changing. Area of coil is not changing, angle is not changing. B also will decrease. If flux also will decrease. How it will oppose the flux? How it will oppose the decrease?
Induced current should be in the same direction as the field.
Bi due to induced current must create a field in the same direction. B direction due to induced current must be in the same direction. So which direction it will be?
It will be in the cross direction.
Okay, so let's look at this. First of all, field is original field is field which is causing flux in the cross sense, and since it has to create in the same sense, even BI also has to be in the cross sense. If it is in the cross sense, what direction it has to be? Clockwise or anti-clockwise? Clockwise. Okay, so I ask one more question now in this. Do you think there will be any force of attraction or repulsion between wire and the loop? Force of attraction / repulsion between straight wire and loop A.
Yes, sir.
Attractive reason why you said yes, Ashray?
So both create fields.
Huh.
On
So
each
there's a
other.
field and there's a current also.
Yes, sir.
So can you tell me which direction will the force act on loop A?
Attractive it will be, sir.
Why? Why force is attractive? Can you give me a reason based on Lenz law? See, what
Sir,
is
since it's being moved away, the force will
Yes.
try to bring them together.
How will oppose away motion? By creating a force of attraction. So what is causing change in flux? What is the cause? What is the cause which is inducing EMF here? Away is away motion. So as the loop is being moved away, I hope this point is clear. Let me write this again. So what is the factor causing change in flux? Factor causing change in flux? Away motion. How does it move in terms of force? What kind of force it must exert to oppose away motion, due to away motion? So it will oppose away motion by applying force of attraction. Pranav,
Yes, sir.
is it clear?
It's clear, sir.
And this logic also have understood. It happens in all sense. Now we can also, not only in terms of current, we can extend the logic in terms of force it will exert. You understood this point as well?
Yes, sir.
Okay, so that's what it is. It is its application is quite wide ranging. Yes, Ashray, you have some query?
So, like, why does the induced field try to oppose the
See,
change?
why does it try to oppose? What will happen if it doesn't oppose? What will happen in that case in the same direction? It means what will happen? It gives slight away motion. If the induced field also create a force in the same direction, it will keep accelerating. It will keep gaining energy, which doesn't happen. It creates a source of energy, which is not, nature doesn't act in that fashion. See, if it is moves away, if you give slight push, it will start moving away. The natural force also is keep pushing it. What will happen? This object will keep accelerating. Wherefrom the energy will come. No, does it make some sense?
Yes, sir, makes sense.
Okay, so that is something. Okay, that's a reason. And okay, now let me ask one more thing here. Okay, this I hope all are understood. Anybody who's not clear would like me to explain some part of it. So what we have done, increasing current, decreasing current, and we also seen what happens if you move it away. The number of ways we can change the flux associated with the loop. What is the other way? One more way we can do that. We can also, what we can do here, if the loops are there, what if the loop is rotated? Suppose we take this case, current is not increasing, current is constant. And what happens if this particular loop is rotated about this axis? What will happen? Do you think there will be induced current when we rotate the loop, or there will not be? What will happen if the loop is rotated? Gayatri, can you tell me what will happen if the loop is rotated?
Flux will change.
Why?
Angle between field and area.
And so we understand this is now the flux is maximum because area is maximum. Area is perpendicular to the field. That's why the flux is maximum now. As we rotate, what will happen? If we rotate, what is flux equal to? Flux equal to B into A into cos theta. Right now, everywhere, when you look at A vector and B vector, what is initially, what is the angle? When loop is lying in the plane, field is perpendicular to the plane. So in this orientation, when they are in the same plane, cos theta is equal to 1. Or minus 1, whatever, in terms of magnitude. So when field is perpendicular to the plane, flux is maximum. So this is not changing. Moment I rotate, what will happen? This cos theta term will decrease, flux will decrease. Flux will decrease. If flux decreases, it opposes by B induced in same sense. That way also you can do it.
So the projection of that loop will be an ellipse, sir? Like,
yes, projection, very good point. Projection of the loop is an ellipse, and if you take projection of the length, that becomes minor axis. So what will happen if this remains major axis? If I rotate, what will happen? I rotate by theta. If you look sideways, if you rotates by angle theta here, okay. If I take its projection, this will become equal to r cos theta. R cos theta will be your B, semi-minor axis. I think people are doing ellipse now.
yes, sir.
Okay, good. It becomes an ellipse. And we can take the area in terms of projection. You can do that. But normally we don't use much in physics, but yes, it becomes ellipse. And for some questions, if you understand that one, we can apply that concept as well. But good observation. Okay. Let's take one more example of induced EMF. How do we generate? Okay, fine, but it can create EMF now in terms of application. Let's try and understand this figure well. What is given here? There's a conducting rod. See, first of all, what are these all dots indicate? Dots indicates a presence of a uniform magnetic field of magnitude B, which is directed perpendicular to plane of figure towards us. This is uniform magnetic field exists in the region. And there's a conducting rod PQ of length L. There's a conducting rod PQ, its length is L. And it is moved on a smooth rail. Why we call this, many books they write a smooth rail. The reason why they write a smooth rail, a smooth conducting rail, because if you talk about rail, it has a large cross-section area, hence resistance is negligible. The smooth rail, so this has negligible resistance, this also has negligible resistance, and even the rod also we take as a negligible resistance. You see where the resistance is. Our resistance R is connected to the end of the rail as shown. So this has negligible resistance, and entire arrangement is placed in a region having uniform magnetic field. So where is the resistance in the whole loop? Resistance is only connected here. Whatever resistance this part have, these resistances are negligible compared to resistance connected here. Okay, so this is a kind of arrangement. Now what are you giving? If this moves, if we give it a velocity v, and assume that this resistance is in form of a bulb. What is this resistance? This is a bulb. When we give it, so suppose with your hand you can push it in a smooth rail, there's no friction. The moment you apply any force in this direction, it will start moving. For the sake of simplicity, let's take this X and Y. So when I move this rail, do you think this bulb will light up? That's what you're thinking now. And let's calculate why it will happen. So is it possible to create, see something what we typically need to light up a bulb? We need a battery, we need an EMF, we need a source of energy. So can we provide this energy in terms of mechanical energy by pushing this rod here, a conducting rod with velocity v? So do you see any reason why this bulb will light up? If bulb has to light up, it means the current has to flow in this loop. There's a loop here. Why would any current flow in this loop here? By moving this rod.
Induced.
Because area is changing. So
area is changing, flux will change. And so basically, so what we notice here, okay, if I push this one, area is changing, and the flux through this loop will change. If flux through this loop will change, there's induced EMF. If there's induced EMF, there's an induced current. That's the reason why we think it will change. Let's examine one by one what will happen here. Okay, let's do one by one, step by step. But prima facie, moment I look at this arrangement, I feel yes, it will create a current. And if it is a resistor here, it will heat up. If it is a bulb here, bulb will light up. Lesson. Resistance of two rays and the rod PQ is negligible compared to R. Okay. Let the rod L have a uniform velocity V. Okay, so what is luminosity V means what will happen? This is something, let me take this distance from here to here. I take this, it is x-axis, this is x is equal to 0. And at some time, it had some coordinate x. So can we write what is the flux here? Initial flux. Flux is B dot A, and in this case, field is uniform. So we don't have to integrate. And what is flux equal to? B vector dot area vector, which is both are in the same direction. So it will be into area. So initial flux will be, what is the area of the loop here? This side length is L, and let's see this distance is X. So at any instance, this is my flux. Are we clear? This is the flux, B into area. So what is rate of change of flux? We can do in a couple of ways.
PLV.
No, flux. We'll write this minus EMF. I'm just calculating EMF. So I'm not worried about the sign. I'll just calculate sign. I'll find out using Lenz's law. So I'm just calculating d phi by dt. This will be d by dt of BLX. What will that be equal to? BL into dx by dt, which is nothing but velocity of the rod. Rate at which the x coordinate of rod is changing, which is velocity. So what is this one? What do we get here? If I move the rod with the velocity v, it is equivalent to creating an EMF equal to BLV in the loop. It will behave as if battery of EMF BLV is placed in the loop. Anvita, are you listening now?
Yes, sir.
Carefully?
Yes, sir.
Okay. So this will behave, it will create a, this is the induced EMF. Then induced EMF will lead to what? Current. How much will the current here and what will the direction of current? If this EMF current is easy, current I will be equal to E by R, which will equal to. Can you mark the direction of current here? Is the flux increasing or decreasing in this case?
Flux is increasing.
Flux is increasing. So what will the direction of induced field? Phi is increasing. Hence, the direction of induced field will be in the same direction or opposite. If it is increasing, it has to be
Opposite direction.
Opposite direction. So if it is dot, it has to be cross. Cross, what is the direction of current? This is the direction the current will flow into the loop. This is the direction in which the current will flow into the loop.
Sir?
Yes?
Sir, how is rate of change of flux equals to E?
The rate of change of flux is equal to?
E, sir.
EMF. That's what he said initially itself. That's the Faraday's law. Induced EMF in a loop is equal to rate of change of current, rate of change of flux in that loop. See,
What was that letter, sir? D phi.
d phi by dt. EMF is equal to d phi by dt. That's what I have taken. EMF is equal to d phi by dt. See, beginning itself, when you look at the lens, if we find in a loop, if current is flowing, it means there must be some EMF. What is that EMF? That is equal to d phi by dt. That's what the law is. It's still not clear, Ashay? You missed the law.
Like,
What
okay,
creates
sir.
EMF? EMF in a loop is equal to rate of change of magnetic field flux in that loop. And what is the EMF? It's just like a battery. So that's why this will have a current. So now what we can do, if you have a galvanometer, we could actually check the current also. We can conduct an experiment, measure the current and see the law is valid or not. Are you understanding? If you have this kind of setup, can we verify this law? Is it possible to verify the law using this experimental setup? Can anyone tell me how would you verify the law using this experimental setup? If you create a known value of magnetic field, length also can be measured. Resistance of the circuit is known. If I give velocity V also I can measure. If I put a galvanometer here, measure the current value. So this is the theoretical value of current. If measure value of current matches, it means my law is valid. And that's how he arrived at the law based on several experiments. Right? Are you getting, Asha, what I'm saying now?
Yes, sir.
Okay. So it creates as if there's a battery connected, but it will light up. So what will happen if you keep pushing the rod here, the bulb will light up. And that's what EMF is, induced EMF. Okay, this has velocity V. So let's calculate what is the induced EMF. We can calculate all these parameters. We'll calculate all one by one. We have calculated what is induced EMF. Induced EMF magnitude. induced EMF magnitude, we'll find the direction. Always we'll calculate EMF separately, direction we'll find out using Lenz law. EMF we have calculated, what is in EMF equal to BLV. Magnetic field, length of the rod into velocity. Thus EMF, and what is the current equal to? EMF by R. And that's why we say as it moves, the resistance of the loop is not changing. There's no resistance associated with this length. Had this rod also length, as it keeps moving, the resistance will change. Are you following my point, what I'm saying here? This part has no resistance. The resistance is only here. So as the rod moves from here to here, the resistance of the loop is not changing. Resistance is a constant. And this will be equal to I will be equal to BLV by R.
What
Which
happens,
direction
sir?
we can mark? Huh?
Velocity is not constant. What happens, sir?
Yeah, we'll come to that part. Instantaneous. We are taking at a particular instance. So at a particular instant, this is velocity, right? And at instant, this is resistance. We'll come to that part later. So this is something. First, let's understand simple part. Then we look at more complicated part. So this is how the current will flow. If current is flowing through this conductor here, this I current is flowing, and this current is it is equivalent to a conductor having current placed in a magnetic field. It will experience a force. A current carrying conductor placed in magnetic field experiences a magnetic force. Can we calculate what is the magnetic force on the conductor PQ? Magnetic force on conductor PQ. How do you calculate force on the conductor?
ILB something.
IL cross B. In this case, both are mutually perpendicular, so it will be equal to ILB only. We will find direction using cross product. So I can write this term, what is I equal to? I is equal to BLV by R into LB is equal to L square B square V by R. Which direction will the force act?
Left.
Now we can, if we are not sure, we can find out right hand thumb rule. This is the direction of L vector, and this direction of B vector is towards us. Or otherwise, if you are not so confident, we can always use I cap J cap. So what will the direction of FB? Direction of FB will be equal along which direction?
What's the right?
L cross B, L cross B vector. L is in along which direction? Minus J cap cross K cap. So which direction? So force will act along minus I cap direction. This direction will force will act. Does force also matches up with the Lenz law?
Yes, sir.
What is causing this what is causing this induced EMF? Rightward motion of the rod. How does it oppose the rightward motion of the rod? By applying a force in the left direction. So which also matches with the Lenz law. So what force? This force will act in the leftward direction, right? So what is the external force needed to keep it moving at the constant velocity? Because there's no friction, there's no loss here. Keep the rod in motion at the constant velocity. Kaushik, can you tell me what is the external force needed to keep the rod in motion with the constant velocity? On its own, it will not move. I need to apply an external force here. What is the external force I need to apply to keep it moving at the constant velocity? Kaushik?
Sir, I'm not sure.
Not sure. Okay. Preetam? Not sure? To move with a constant velocity, what has to be net force something moving with a constant velocity? Net force is 0. Which are the two forces acting on this rod here? Magnetic field force, magnetic force and external force. If I have to keep it moving at a constant velocity, it means net force is 0. If net force is 0, it means external force has to be equal and opposite to FB. So what is external force needed? Same as this. Kaushik, have you understood what I said now?
Yes, sir.
What did I say? Tell me, repeat that point.
So to have the constant velocity, net force should be 0.
0. So which are the forces acting on the rod? Magnetic force, due to current flowing and the magnet, and external force. They have to be equal and opposite. So this is the force I need to apply to keep it moving. Okay. Now I'll calculate two more things. I have enough time. Yes. So what is the power required by external force? What is the power required to keep the rod moving? What is power equal to? Force dot velocity. Both are in the same time. For power is equal to F dot V. And what is F dot V will be equal to? This is a force. I multiply velocity. The power required will come equal to L square, B square, V square by R. Karthikeya, are we clear up to this point?
Yes, sir.
Pranav?
Yes, sir.
Gayatri?
Yes, sir.
Are you sure? So I'll ask something more. So now Gayatri, let me ask something. Can you tell me what is the power dissipated in the resistance? See, the current is flowing, there's a resistance here. So there's a loss of heat here, but there's heat dissipation here. What is the power dissipated in the resistor? Can you tell me what is the power dissipated or power lost in the resistor? Gayatri? What happened, Gayatri? Suddenly become very quiet. What is the power dissipated in the resistor? Do you have any formula which tells you what is the power dissipated in any resistor? Gayatri?
Sir.
What is the power dissipated in the resistor? Any resistance, what is the loss of power? How much power it consumes? We can also use the part, what is the power consumed in a resistor? What are three formulas we know for power dissipation? Anvita, what is the power dissipated in the resistor?
I don't know, sir.
Very good. We don't know what is power dissipation. Okay. Disha, what is the power dissipation in the resistor?
I square R.
So it's such a difficult question. Gayatri, such a difficult question to answer. Anvita, power dissipation we don't know. Does it, Anvita? Are you there? Say yes or no.
Yes, sir.
Is this question, answer to this question, did it need any concept?
No.
So why did you not answer? Tell me then. You should ask that question yourself, why I'm not able to answer, and how would I correct that one? This is a pretty straightforward question. And so do have value of I somewhere? I have calculated I value. Can I calculate power dissipated? Yes, I have I value, I have R value. So let me put those values here. I square R, it will be equal to BLV by R whole square into R. How much this come to? 1 R comes cancel, it comes equal to B square L square V square by R.
So the complete work done is getting converted into...
Yeah, because there is no loss of energy anywhere. So where from this
100%
energy is coming in the resistor? Energy is coming because of, so what is happening in the whole process? Mechanical energy is getting converted into electrical energy. So what we notice here, since if it is frictionless here, because it is frictionless, that's why these two are equal. Had there been friction, this would not have been equal. So what we find here, power dissipated is equal to power delivered by external force. So let's look at this each part, each all sequence. Is the sequence clear, everyone?
Sir?
Yes?
Sir, I didn't understand the last part.
Yeah, I noticed this term and this term are equal.
Yes, sir. So like what does it indicate, sir?
What does it indicate? So what is happening? I am supplying this power where this energy is being supplied with external force, which is exerting a force on the rod. Okay. And where is this energy going? If you look at energy
Heating up
balance
the
again,
resistor.
where is this energy going? This is power because there's no friction. It's not getting lost in friction. This kinetic energy of this rod is not changing. It is moving at a constant velocity. There's no other potential energy associated. So where is this energy going? Logically, also, I would have expected whatever work is being done here, that work is getting converted to some other form. It is manifesting in some other form. What is other form it is turning it into? Other form it is turning it into is equal to heat energy in the resistor. Does it not make logical sense?